Hey there, this video is all about the definition of the derivative. Now, in earlier lessons, you might have gotten a glimpse of what the derivative is and how it relates to rates of change. So we're going to go into a little more depth and get some algebra involved to actually figure out a function which represents our derivative. So in this video, all right, we've got 3 examples that we'll go through, and then an introduction before all that, though, to get us an idea of what our derivative is all about. Okay, so first of all, the connection between the instantaneous rate of change and the derivative is that a derivative is a function that describes the rate of change for any possible value, and we typically call the IROC our value at a certain point, and we've talked about that before. Now, before we had this limit as x goes to a of f of x minus f of a over x minus a, all right, and we called that the average rate of change. I don't know if you remember that. And then adding the limit made it what's called an instantaneous rate of change. So this f of x minus f of a over x minus a becomes an instantaneous rate of change when we add the limit part to it. And we call this our derivative. All right. Now, we can certainly use that definition to come up with all of our functions which represent derivatives. But there's going to be another definition of the derivative that we're going to use more often than others, what we'll call the limit of the difference quotient. And that is this limit right here. Limit as h goes to 0 of f of x plus h minus f of x all over h. So I drew a little picture over here off to the side, which gives us an idea of what that means here. So when we have our 2 points x and x plus h, all right, what we're really doing is we've got 2 points that are really, really close to each other, all right, and we're finding the average rate of change of the function between those 2 points. So at f of x plus h and at f of x. All right, so this numerator is just the difference in the function divided by our difference in x. Well, if we're going from x to x plus h, we've moved h units. All right, so our change in x is just h, and that goes in our denominator. So what makes this a limit, or excuse me, what makes it a derivative is we're going to look at the limit as h goes to 0 of this function. All right, as these points get closer and closer to each other, we make this into what's called an instantaneous rate of change. So the statement that I just talked about, f prime, is what's called the derivative of f, and is, like I said, pronounced f prime of x. And this isn't the only notation that's available to us. This is what we might call our Lagrange notation. But we've also got our Leibniz notation here, which is the dy dx. Oftentimes you'll see this written as y prime, or the derivative of f with respect to x. Right? That would be how we pronounce this one here. Or you could even just say the derivative with respect to x of f of x, so the dx is the only part there. So the d is the operator, which tells us to take the derivative. So as an example, we want to find the derivative of f of x is equal to x cubed minus x. All right, so we start out with our definition. So the limit as h goes to 0 of f of x plus h minus f of x divided by h. And you'll see in just a second why we use this definition over the others. Well, it makes the algebra a whole lot easier. So when I plug in x plus h into the real function, x cubed minus x, I get x plus h cubed minus x plus h minus what we get when we plug in f of x, which is x cubed minus x. So all I did was I plugged in x plus h and x into my function here. Now you'll notice there's a lot of algebra going on here, so we could expand our terms. X plus h cubed expands out when you work it out to x cubed plus 3x squared h plus 3xh squared plus h cubed, and then when I distribute my negative, I get a minus x minus h, and then all minus x cubed minus x. And all of that is over h. So it looks like a mouthful, but basically all we did was we expanded our terms here. All right, so onto another page here. We can actually cancel out a whole lot of terms from the previous page here. So notice I got an x cubed minus an x cubed, and I got a minus an x, and I got a plus x when I distribute my negative. So what we end up with is terms that are nothing but terms with h's in them. So I've got a limit as h goes to 0 of 3x squared h plus 3x h squared plus h cubed minus h. So all terms should have an h in it if you're doing this right. Because what we can do is we can factor out an h, or say that we divide by an h, all right, and we're left with 3x squared plus 3xh plus h squared minus 1. All right, so all I did was I took out an h of each part of this. And now, of course, we took out the issue that was giving us the divided by 0 issue, right? And so now we can plug in h equal to 0. Well, h equal to 0 will make this term go to 0, and we'll make this term go to 0. So all we're left with is 3x squared minus 1. So this is a really amazing and remarkable statement because it says that no matter what x you choose for the function x cubed minus x, f prime of x is always 3x squared minus 1, which is going to allow us to find the derivative or the slope at any value, I don't know, like 2. So let's say you plug in 2 into our derivative here, and we get 3 times 2 squared minus 1, which is 11. So this is going to easily allow us to find out what our derivative or our slope of our tangent line is at any value. All right, so let's try it again. Find the derivative of f of x is equal to square root of x. So here we got f prime of x, all right, and we're going to take square root of x and plug both x plus h and x into it. All right, so if we think about our definition, limit as h goes to 0 of f of x plus h minus f of x all over h. So here I've plugged in my x plus h, and here I plug in my x. And we want to see what happens as h gets smaller and smaller and closer to 0. So if you remember when we first started studying these limits, I said one of the ways that you can evaluate this is by multiplying and dividing by the conjugate. In this case, the square root of x plus h minus the square root of x. Well, the conjugate of that is the square root of x plus h plus the square root of x. Right? And when I multiply and divide by that conjugate, you'll notice I get an x plus h minus an x in my numerator. So it's a difference of 2 squares, right? Which reduces down to just h. In my denominator, I'm going to leave that alone as h times square root of x plus h plus square root of x. All right, and now I can reduce out that h, and I'm left with limit as h goes to 0 of 1 over square root of x plus h plus square root of x, which becomes 1 over 2 square root of x. It's a very common derivative that we'll be using quite frequently, so kind of put that in your memory bank. Don't worry, you'll get plenty of shots at it. All right, one last one here for the video. Find the derivative of f of x is equal to 1 over x. All right, again, we want to plug in x plus h into our function to find the derivative. Limit as h goes to 0 of 1 over x plus h minus 1 over x all over h. We can simplify our fractions in our numerator by finding a common denominator. So on the left, I get x over x times x plus h minus x plus h over x times x plus h. So I just found a common denominator, and everything is over h. So one thing to keep in mind is that if we're dividing everything by h, that's the same as multiplying by 1 over h. And then beyond that, I can simplify my numerator up here by saying I've got x minus h if I distribute my negative. So altogether, I have limit as h goes to 0 of negative h over x times x plus h times 1 over h. The h's cancel out, and I'm left with limit as h goes to 0 of negative 1 over x times x plus h, which is negative 1 over x squared. Again, a really remarkable statement. Okay, let's go the other way now. The following limits represent f prime of a for some function f and some number a. Can we identify what the function is and what the value is that we plugged in? So in this case, I've got limit as h goes to 0 of the square root of 9 plus h minus 3 all over h. And we want to try to see if we can match that up with an f of x plus h minus an f of x all over h. So in this case, we notice that we've got a 9 plus h inside of a square root. So it appears like we've plugged in a something plus h into the square root. That's what we're looking for to see if we can spot what function this is. And indeed, we would say the function is square root of x. 9 plus h is the input for the function here. Okay? So once we identify that what that is, then it looks like we've plugged in something for x in this function. And the value for a, the value that we plugged in for x, would be 9. All right? So what we've done is we found the derivative of square root of x at the value of 9. Another way that you can know this is f of x is the square root of x. And if we plugged in 9 for x, we get the square root of 9, which is equal to 3. All right? So this matches. So this limit represents the derivative of the square root of x at the value of 9. Okay, one more here. The following limits represent f prime of a for some function f and some number a. Identify f of x and a. So we've seen this kind of limit before, haven't we? Limit as x goes to 4 of x squared minus 16 over x minus 4. Now, this is a different form of the derivative, but it's still the same idea. We've got a function, x squared, which matches up really nicely with that f of x there. And we've got an a value, which is equal to 4. So what this limit has told us is we want to find the derivative of x squared at x is equal to 4. Well, we're going to be able to show the derivative of x squared is 2x. And so if I plug 4 into that, I get the derivative at 4 is equal to 8. That's interesting. Well, hey, we should know how to find this limit. Remember we talked about factoring and canceling and all that sort of stuff? Well, x squared minus 16 is x minus 4 times x plus 4. All right, and if I reduce this down, I get limit as x goes to 4 of x plus 4, which is equal to 8 when I plug in 4. Right? So what we just found is this limit that we've known for a while was actually the hidden limit for the derivative of x squared at 4. Whoa, who would have known? It's so mysterious. All right, so in summary, we're going to use the definition of the derivative to find out a lot of derivative functions. Look forward to that. And remember those good times with limits. They're back, and we're back too. We'll see you on the next video.